You know, have you ever wondered what's the most efficient way to build something? Or how a company can get the most profit with, say, limited resources? Well, these aren't just business school questions, they're actually math problems. And today, we're going to dive into the powerful calculus tool that's designed to find the absolute best answer to questions like these. It's called optimization. And that right there, that's the core idea, isn't it? I mean, we're not just looking for a decent route. We want the fastest route. We don't want to make some profit. We want to make the most profit possible. So think of optimization as the mathematical engine that turns calculus from this abstract theory into a really powerful practical tool for making the best decisions. So what does that actually mean? Well, imagine any situation as a kind of landscape, with hills and valleys. Optimization is basically the process of using calculus to find the exact coordinates of the highest peak, that's your maximum, or the lowest valley, that's your minimum. It's all about mathematically pinpointing that single best-case scenario. Now, I know this might sound a little complex, but don't worry. There's this beautifully simple and reliable roadmap for solving almost any optimization problem out there. We're going to break it down into a really clear 3-step strategy that you can pretty much apply every single time.
Okay, here it is. First up, step 1, the primary equation. Just ask yourself, what are you trying to maximize or minimize? Is it area, volume, profit? Whatever it is, that's your target. Second, the constraint equation. This is your limitation. What's holding you back? A tight budget? A set amount of fencing, maybe? This part is key because you use this limitation to rewrite your primary equation so it only has one variable. And finally, the fun part, calculus. You find the derivative, you set it to 0, and you solve. That's it. That's how we find the exact top of the peak or the bottom of the valley.
All right, so that's the theory. But honestly, the best way to really get this is to see it in action. So let's put this strategy to work with a classic problem that you might have seen before, the farmer's fence. So here's the setup. We've got a farmer who has 2,400 feet of fence. They want to make a rectangular pen, but one side is right up against a river, which is pretty handy. It means we only need to fence 3 of the 4 sides. The goal is simple. Find the dimensions, the length and width that will give us the biggest possible area inside that fence. Okay, let's fire up our strategy. Step 1, the primary equation. What are we trying to do? Maximize the area. So let's call the 2 sides that are perpendicular to the river x and the side that's parallel to the river y. The area formula is easy, right? A equals x times y. Now, for step 2, the constraint. Our limitation is the 2,400 feet of fence. That means the 2 x sides plus that 1 y side have to add up to 2,400. So our equation is 2x plus y equals 2,400. Now this next bit is the crucial link that ties it all together. We take our constraint equation, 2x plus y equals 2,400, and we just solve it for y. Now we can plug that right into our area formula. And just like that, we've gone from an equation with 2 variables to one really powerful formula for area that depends only on the length of side x. Now we're ready for some calculus. And here comes step 3. We take the derivative of our new area function. Now remember, the derivative just tells us the slope of our function's curve at any given point. So at the very, very top of the hill, at the absolute maximum area, the curve is momentarily flat. Its slope is 0. So to find that peak, all we have to do is set our derivative equal to 0 and solve for x. We do a little bit of quick algebra, and boom, we find that x equals 600 feet. But hold on, we're not done yet. We got to plug that value of x back into our expression for y. That gives us a y value of 1,200 feet. So there we have it. The optimal dimensions are 600 feet by 1,200 feet. And what do those dimensions actually give us? A massive 720,000 square feet. Any other shape like a long, skinny rectangle would have given a much smaller area using the exact same amount of fence. This is the real power of our 3-step method, finding that one single best solution. Okay, that was a great start, but this strategy is way more versatile than just fences. Let's level up with a couple of new puzzles. We'll see what else this can do, and we'll even uncover a super common mistake you'll definitely want to avoid. All right, puzzle number 1. Imagine you have a 12 by 12 inch square of cardboard. You're going to cut identical little squares, each with a side length of x from all 4 corners. Then you fold up the sides to make an open-topped box. The question is, what size square x should you cut to get the absolute maximum possible volume? So, we follow the exact same process. As you can see, the volume is the height, which is x, times the length and width, which are both 12 minus 2x. This gives us our primary equation. Then we just run that through our calculus engine to find the derivative, the prime of x. The process? It's exactly the same. So when we set that derivative to 0 and we solve it, something kind of interesting happens. We actually get two possible answers. X could be 2, or x could be 6. The math gives us two critical points. So, which one is our maximum? This brings us to a really crucial point and is super common mistake. You have to always check the logic of your answers. I mean, think about it. If we let x equal 6, that means we're cutting a 6-inch square from each corner of a 12-inch sheet. Well, that leaves literally no cardboard left to fold up. The volume is 0. That's got to be the minimum. Therefore, the maximum volume must come when x is equal to 2. Let's try one more, this time a more abstract problem. No boxes, no fences. The problem is, find two positive numbers that multiply to 100 and whose sum is as small as it can possibly be. And once again, the strategy holds true. Our primary equation is the sum, s equals x plus y. Our constraint is that x times y has to equal 100. We solve for y, substitute it in, and we get our function just in terms of x. From there, it's pretty straightforward. Find the derivative, set it to 0, and the math quickly points us right to the answer, x equals 10. And since x is 10 and their product has to be 100, well, the other number must also be 10. So there you have it. The two numbers that multiply to 100 with the smallest possible sum are 10 and 10. It's a simple, kind of elegant solution that we found with our powerful strategy. So, we've enclosed a field, we've built a box, we've found some numbers. What's the big takeaway from all of this? What's the one core lesson you should remember? It really all comes down to this reliable strategy. First, identify your primary equation, what you want to optimize. Second, find the constraint, your limitation, and use it to simplify things. Third, apply the calculus, find the derivative, and set it to 0. And as we saw with that box problem, don't ever forget the bonus step. Always, always check that your mathematical answer actually makes logical sense in the real world. And really, that's optimization. It's so much more than just a chapter in a textbook. It's a powerful way of thinking. It's a method for finding the best possible outcome when your resources are limited. So take a look around your own world. From planning your day for maximum productivity to minimizing waste in a project, what could you optimize? Thanks for joining this explainer.